The broadcast is now starting. All attendees are in listen-only mode.
Hi, good afternoon, everyone, and welcome to today's webinar sponsored by the U.S. Department of Energy. I'm Sarah Bushy, and I'm here with Devin Egan. We're broadcasting live from the National Renewable Energy Lab in Golden, Colorado. And we're going to give everyone a few minutes to call in and log on. But while we do that, Devin's going to go over some of the logistics, and then we'll get started. Devin?
Okay, good afternoon. First of all, you have two options for how you can hear today's webinar. In the upper right corner of your screen, there's a box that says audio mode. That will allow you to choose whether or not you want to listen to the webinar through your computer speakers or over the telephone. As a general rule, if you can listen to music on your computer, you should be able to hear the webinar. If you have questions during the webinar, please use the questions pane in the right-hand box on your screen. In there, you can type any question you have during the question and answer segment at the end of today's presentations or throughout the presentation. After today's webinar, you'll be prompted to complete a short survey. We ask that you take a few minutes to submit your answers once the webinar has ended. Today's webinar will be posted online on the Community Renewable Energy Deployment website. Presentations will be posted later today, and recorded video files and transcripts should be posted in the next 1 to 2 weeks. With that, I'll turn it back over to Sarah to talk about today's webinar and our overall series.
Thanks, Devin. And we'll send an email out once the audio is posted. Yes, so everyone should get that. So today's webinar is the fifth in a series of U.S. Department of Energy Community Renewable Energy, or what we call ComRE, success stories. Each of the webinars features communities that are successfully implementing renewable energy technologies all around the country. So the ComRE project is a more than $20 million effort funded through the American Recovery and Reinvestment Act of 2009 to promote investment in clean energy solutions at the community level, and also to provide real-life examples for other local governments, campuses, and utilities to replicate. 5 community-based renewable energy projects receive funding from DOE through the ComRE program, and that's in Vermont, Wisconsin, Colorado, and California. This webinar series is a part of the broader support that's provided to communities under this project, and provides success stories from both the ComRE grantees and then also other communities that are leading the way in renewable energy. During today's webinar, we'll focus on the experiences integrating renewable energy into district energy systems at Ball State University, Indiana, and in the city of St. Paul, Minnesota. Like these two communities, Montpelier, Vermont, which is one of the ComRE grantees, was awarded funds by the Department of Energy to install a central district energy system fueled with locally sourced wood chips. You can learn more about Montpelier's project on the EERE website by going to eere.energy.gov and just searching for ComRE, or Community Renewable Energy Deployment. So without further ado, I'd like to introduce our first speaker, Jim Lowe. Mr. Lowe is the Director of Engineering, Construction, and Operations at Ball State University. He received a Bachelor of Science in Mechanical Engineering from Kettering University and is a registered professional engineer in Indiana. Jim, we're going to turn it over to you right now.
Sarah, Devin, thank you. And thanks to US DOE for providing this opportunity. I never grow tired of telling this story. It's a great story to tell. Can you see the screen okay? Sarah?
We sure can. We sure can.
Okay, great. All right. I've got to talk rather quickly. Apologize ahead of time because I had 30 slides. I've never figured out how to make this shorter and tell the story. So I've got 30 slides. I'm going to slide through it really quickly. I segregated the story into our existing heating and cooling system so you have some idea of how our system functions today. Go into the path that led us to geothermal, talk a little bit about design and construction, and the benefits of the geothermal project. So moving on to the next slide, and I'm not moving the slide. What am I missing?
Jim, you should be able to just click on your presentation. There you go.
Got it. Okay. The university really opened in 1899, and I tell this story from that point because I'd like to point out the fact that this original building, which is the administration building, actually had a boiler in the basement. We dumped coal down to the boiler, we made steam, and the steam was used in a radiator. So we've been burning here at the university coal to provide heating means for the campus since 1899. The campus actually opened and closed about 3 or 4 times before in 1917 the Ball brothers came to Muncie because of the natural gas resources, and that's the irony here, is they came to Muncie to reach into the ground to grab natural gas, which is actually somewhat depleted today in this area, but today now we're reaching into the ground again to take advantage of the fact that the ground can be a thermal storage unit, if you wish. But in the 20s then we expanded as a university, and you can see that we have the administration building here, and the campus just kind of grew in this south, what we call South Quad area, and over in the area to the, I'd say the right here, we have our central plant that was first established back in that time period. And we continue to expand that system as the campus grew. So expanding steam throughout campus, steam was used to heat our buildings, but somewhere in the 50s and the 60s, as all universities understand, steam then was used through a converter to actually make hot water. And that's predominant use of our steam on campus today, of course, is for heating buildings, but it's used through a converter to make hot water. And how we do that, how we make that steam, is through the use of 7 boilers. Those boilers were installed, as you can see here with this slide, many years ago. The coal boilers, 1941 and 1955, which is a tribute to those who have been around this university for many decades, who've done a great job of maintaining boilers. And then we have 3 natural gas-fired boilers that serve basically for us for peaking. So our gas boilers make about 15% of our steam, or did, and the coal boilers were used predominantly because the coal was cheap, and that produced about 85% of the steam we consume on campus. Well, this is an exterior photo, of course, of that heat plant operation. As you can see here, the stacks. I throw the arrows up there to point out that our plant, probably much like other plants at universities, have an efficiency that's probably around 75% burning coal. So 25% of your heat value is lost up through the stack. So you pay $1 for energy, you get 75 cents back. And then yet behind this plant, we have the chill water plant that was built, in our case, in 1960, that is producing chilled water for the campus, so bringing back heat, and through these cooling towers, we're dissipating thermal energy into the atmosphere. So this plant is throwing 25% of the heat value coal up the stack, and this plant is literally throwing thermal energy away, and the 2 plants don't connect, which is a challenge that I've thought about for years around here, and how we could actually connect and gain advantage by connecting these 2 operations. And I'll talk a little bit more later on about the simultaneous heating and cooling that's going on, but the beauty about the geothermal system, it kind of connects those 2 operations together and allows us to recycle thermal energy. And the numbers over here, you can see about the size of our plant. We produce 700 million pounds of steam a year and about 25,000 ton-hours of chilled water. We burn about close to 36,000 tons of coal a year. And you can see the pollutants that are produced because of that burning of coal. And down below here, you can see that we're also now, as many universities are, subjected to boiler MAC, which is 187, unless I've lost track of it, hazardous air pollutants. And the one that would kick us into issues with boiler MAC would be the amount of mercury that we would send up the stack through burning coal. Well, a combination of events led us to, or conditions I should say, led us to the decision in 2004 to replace our coal-fired boilers. And you can see those issues here. You know, the age of the boilers, the campus has grown since that 1920 period to today, where we're over 7.2 million square feet over about 1,000 acres. Our boilers, because they are the age they are, have basically degraded. They just can't produce the nameplate capacity. We have restrictions placed upon us by Title V permit here in Indiana. The amount of coal we can actually burn is, the max ends up being about 36,000 tons. And now we have boiler max kicking into the equation as well. And so all this led to the decision in 2004 to replace our coal-fired boilers. And so we went to the state of Indiana, as all public institutions have to do, and requested an appropriation in the amount of $45 million, which was in fact appropriated. And that 45 was based upon estimates we were receiving in 2005 through 2006, that time period, for a boiler that is a CFB. And a lot of universities are familiar with this type of boiler. We chose this boiler at that point in time, this being about 2007 or 8, because it had the ability to burn alternative fuels. So although we were moving forward with what folks would consider a solid fuel burning or coal-fired boiler in the CFB, we were going to start off by burning some type of biomass. We weren't sure where we would get this continual supply of biomass, but that's what we had planned to do, with the hopes that we would flip this, and someday it would be perhaps 70% alternative fuels and 30% fossil fuels, if not someday 100%. The other thing is that this type of boiler is a lot more efficient. It would reduce our cost by about 15%. We're not, in terms of fuel, we're not sure where would lead us into our operating costs, because it's a little more maintenance, I guess, heavy, because of the handling equipment and so forth. And then we have the fact that after we evaluated all this, our cost of our project escalated to the $65 to $70 million range. In some cases, maybe a little bit above that. If we go back and look at it today, it's probably $75 million by 2008. And why did that happen? We think it's because of the issues that were going on with the escalation of iron. Our product, or our CFB, would be made in China, and costs were really increasing dramatically, and they had a 2-year backlog of orders. And there was a point in time when we even weren't sure we would find somebody that would want to make this boiler for us, because it was so small, there wasn't many people interested. And we think that combined to increase the cost. So we went back to the drawing table, understanding that we only had $45 million. The cost of that particular option was in the $65 to $70 million range. So I use this to guide through what we considered, and those considerations included, what other way could we produce steam by burning coal? You could go back to a stoker boiler, but we didn't want to go back to the old technology. We're certainly not going to get into burning petroleum, which was even more expensive and problematic. We looked at natural gas, as many institutions have done, and we'll still burn gas here, as a matter of fact. But to go 100% natural gas in your production of steam was very risky. We life cycled that option, although it had a very low capital cost compared to these other options. Our evaluation at the time, certainly gas is a little less expensive today, would indicate that within a short period of time, perhaps 10 to 12 years, you wouldn't have liked your decision going to all natural gas, because the operating costs would overcome that capital outlay. Certainly we're not going to consider nuclear. It's just not practical. So we looked at this small part of the energy equation here that's called renewable. And remember, we were looking at a renewable option with the CFB. So we looked at what other ways could we produce some type of product to heat our buildings that would use a renewable, when the idea of geothermal was tossed out on the table. And so that began the quest to do some research. And now we all knew what geothermal was, but there was no real understanding of how you would capitalize on a geothermal concept or process in a university setting, and in particular for me and others that run a central plant, how would you make it a district heating system? And we're actually looking at heating and cooling with the system. And so we reached out to other universities through our survey capability, and I received a lot of good information from a lot of different universities. We then reached out to other entities, the group in the middle from IGSPA down to the U.S. Department of Energy. Certainly talked with them quite a bit, including NREL, Oak Ridge Labs, and NGWA, and obtained whatever information we could, snippets of information from those organizations that would be valuable to our quest to develop a proof of concept and how to move to a district heating and cooling system with geothermal. And they even looked at some installations, the Galt House, Stockton University, AUL, One American Building. The One American Building is located in Indianapolis. Two of these systems are open or water systems. They even spoke to Dr. Kavanaugh and Rafferty, who write books about big G and little g type systems. Well, we moved from there to developing a proof of concept to determine if this really was feasible for Ball State. And the real thing I was keen on was making sure that we could make a district system out of this type of system. We found out you can, in fact, produce both hot water and chilled water with the type of system we've developed. Yes, it had a bigger cost outlay, $75 to $80 million, but with this $2 million savings that we're estimating we will gain, it was worth the difference in the upcharge from that CFB operation to a geothermal operation. And we realized we didn't have all the money we needed, but we were willing to do as much as possible. Even that meant only doing half the campus and working year after year with the savings, pouring that back into capital to totally convert the campus to geothermal. And then we reached out in 2009, the U.S. Department of Energy, and obtained a $5 million grant. That 5 plus the 45 that we got from USDOE helped us to get past the midpoint of this quest, and we're actually working into what we call phase 2 of the project because of that funding that was made available. And we hope in the spring we'll have rest of the funding in place through perhaps another state appropriation. Well, moving forward, we looked at different types of systems. These systems include the one you see in the lower left-hand corner here, which is an open system, much like that One American Building. All the other systems that are wrapped around that here on this little sketch are closed systems. The system that we selected is the one in the upper left-hand corner, and the reason is our system is so large. The only way to obtain, logistically obtain the capacity we need is to go deep or vertical. We're installing 3,600 boreholes, and in itself, with a 15-foot spacing, is about 25 acres of land that we need to install all the boreholes. And the other types of closed-loop systems, the space just wasn't available. Well, moving on, the type of system, again, is a closed loop. You can see in the left photo here, before it was actually covered over. The boreholes are spaced 15 feet apart. They're headered together with the idea that with this cross-section, as many of you well know, we're flowing water into the ground through this piping system and back out. So it's just circulating through the ground. Sole purpose is to transfer thermal energy, either into the ground or back out of the ground. It all depends upon the time of year and the load you have on your campus. And I wouldn't be the engineer in me if I didn't show you the laws of thermodynamics. Didn't realize that I went to college I'd actually use this someday, but we're actually capitalizing on all this. Where second law is the actual principle by which this endothermal energy is either flowing into the ground or back out. Third law goes to the fact that the ground is 55 degrees, but it still has a great potential for thermal energy. And the great one is back to that point I made earlier when we have two separate plants, the chill plant and the steam plant, and the two don't connect, so I have no way to recycle energy with that type of operation. Now I get to capitalize on conservation of energy here, because what we're doing with our operation, which I'll explain in a minute, is we're actually bringing thermal energy back from campus through our chilled water loop, moving it through our refrigerant system and our heat pump chiller, inserting that on the discharge side or the hot water loop, and we're reusing it in buildings that may want that thermal energy for heating purposes. Well, moving forward into construction, we broke ground in 2009. Senator Lugar was here, big proponent of our project. We were successful by the fall of 2010 in installing the first 1,800 boreholes, or about half of the boreholes we're going to need ultimately. And by the December 1st time frame, 2011, so about 1 year ago, we actually had the system up and running. It's been running since that point in time, producing hot water and chilled water for our campus. And the efficiencies are phenomenal with that operation. Well, to give you an idea of how the drilling works, here are the rigs that are being used. On the left-hand side, you can see an actual photo. The production is about 1 borehole per rig per day. The cross-section would show that we are using a mud rotary drilling method that helps stabilize the actual borehole as we drill down 400 or 500 feet. And in this case, with the mud rotary, it also reduces the amount of water that is basically brought up to the surface. It's a muddy mess the way it is, but it's a much better process for what we were doing here with a number of boreholes and trying to maintain control of the site. Well, then, after the boreholes drilled out, the piping is installed. The photo you see on the left-hand side is really a photo of a double loop being installed. That was done on the north side of campus. On the south side of campus, we're only installing 1 loop, and I'll explain why here in a moment. The right-hand photo will show you the fact that then once the tubing is installed in the borehole, it's filled back in with a grout mixture that's really a bentonite plus sand type mixture that fills this all back in again, allows the thermal energy flow and blocks the flow of water from the surface back down into the aquifer. What's key about the borehole design is ensuring that you have the correct spacing so that your thermal energy flow doesn't have a detrimental effect from one borehole to the next, which is a study that we want to undertake here with using our geology department staff and the graduate students. But the point out here is that 3,600 boreholes is about 1,000 miles of high-density polyethylene pipe that's inserted in the ground to get that total capacity we need for our campus. Back to the actual spacing of the borehole, I like this chart to just convey that the yellow shows that we are 55 degrees below the surface, and the key is maintaining over the years of operation of the system that level sinusoidal wave, so it's neither going up or down, which would indicate some type of detriment to the ground. And you can actually pick the time of year by looking at the sinusoidal wave. The peaks are the winters, or the summer, excuse me, and the valleys are the winter where we're actually extracting heat out of the ground, so it does vary the temperature somewhat. The key to the operation is our heat pump chillers that produce simultaneously hot water, cold water for use out on campus. The 150-degree water is produced by these chillers, and the 42 is pretty much the temperature that we produce on campus with our old chillers. The 150, I want to point out here, is a little bit less in temperature than what some of our buildings reset temperatures wanted years ago. Some of our resets were 180 degrees. We did test our theory out here one winter before we moved forward, took all our buildings, maxed the reset to 150, and proved over one winter 150-degree hot water could work. Yes, down to about 0. There's a few buildings that were unhappy or cold, but that's the point in time when perhaps you'd turn the steam up a little bit through your old heat exchanger and boost the water temperature a little bit. I see I'm getting really close on time, so I'm going to rush here a little bit. This is basically a cross-section of, or a working diagram of those heat pump chillers. We're producing hot water on the condenser side, chilled water on the evaporator side, and what's remarkable about the project is is developing a coefficient of performance nearly 7. So one input of energy gets 7 out. When you combine the operation together, this is a diagram of how it all connects. On the left-hand side, you see the borehole filled connecting the supply and return line to the central plant where the heat pump chillers are located. We make chilled water and hot water to send to campus to the various buildings where that water is used through a typical air handling unit. And the air handling units in most cases did not change. They remain the same. We just plugged and played. You can see the installation of the hot water pipe. Again, a whole new distribution system on campus that didn't exist. It's a whole new supply and return hot water loop with an insulating product around the pipe to make sure the water temperature was maintained. 10 miles of new piping on campus for that distribution system. Again, the air handling units didn't have to change. The green shows chilled water goes in a coil. The yellow shows I got hot water going into the hot water coil. And this unit doesn't care, doesn't know it's getting its supply of chilled water and hot water from the geothermal process. A quick diagram of how this was all connected. The old process is a heat exchanger, as you see on the left-hand side in the middle of this diagram. Steam goes in, condensate comes out. We've got a circulating loop of hot water that goes over to the air handling units. All we had to do was reach into the building with our new distribution lines, tap into the return side of that equation. We even keyed off and went to another heat exchanger where we could preheat domestic water, trying to find multiple uses for that thermal energy that we're producing. The great thing about this schematic and how it would work if the geothermal system for some reason would go offline during the winter, we can simply go back to steam, and we have steam for backup to all these buildings that's there, turn it on, and we got heating by the old method of steam, in this case though produced by burning natural gas. Half our campus is converted. The green buildings represent the buildings that have been connected to the system. About midway in this diagram is Riverside, which basically separates the north and south side of campus. So the north side of campus is complete. The south side of campus is the portion of the project that we would consider phase 2. Most of that work will be completed when we get a new appropriation, perhaps this next spring, from the state of Indiana. Benefits, starting to look at emissions. We'll nearly reduce our carbon footprint in half with the 75,000 ton reduction. All the emissions issues with coal are gone, and the great thing is Boiler Mac is now for Ball State, we're in compliance because we're not burning coal, and we will not have to be subjected to adding emission control equipment unless someday the EPA regulates natural gas in some form. The other benefits of the reduction in energy use, it's the COP being 7, will allow us to, number one, not burn coal and buy very little additional electrical power to run our pumps and our heat pump chillers. The resulting factor is a 40% reduction in our energy use on campus, 185,000 BTUs per square foot per year to 110. The other benefit is just 36 million gallons of water. That was an aha moment about a couple months ago when we say, hey, we're going to shut our cooling towers down. We no longer need to run them. And running cooling towers for us has equated to about a 36 million gallon a year usage in water. We have had a lot of visits and certainly would welcome anybody that's interested in coming to campus or calling to do so. Reach out to us. We're more than happy to convey to folks our lessons learned and how our system is actually constructed. We've had, besides universities, we've had a number of entities. I had a design firm, Korea, in here was about 2 months ago, folks from Tokyo, folks from Germany, just a number of people who want to reach out and learn a little bit about how this system works and the little lessons we've learned about the process. And those lessons learned are more in the constructability of the project, and that's purging. Once all your piping's installed in the ground, we found that you really have to get your velocity pressure up to push anything that got into the piping system out of the piping system. That includes rocks and so forth. Ductile iron pipe, we had an asphalt coating specification. That's been taken out of our spec. Problem is when you get debris in the pipe and you turn it on and get those velocities up, you scarify that. you remove the asphalt, it gets moving into the buildings, and we have to, through our filter systems, constantly change our filters on our strainers. And it's gone today, but it's an issue that you wouldn't have to deal with if you didn't specify asphalt-coated piping. And we use that on our ductile iron for our hot water side. We've gone from the double to the single loop arrangement. The reason we did that is the installers, biggest part of our construction cost, $30 million, is the boreholes. We certainly listened to our drillers. They told us it was problematic trying to get 2 loops in 1 hole. We thought it was a great advantage because we get a little bit additional capacity out of 2 loops in the same borehole. We've gone to the single 500-foot deep versus the double 400-foot deep, and the grout is a little bit more stout, 1.2 versus 0.69 on the double design. The grout, we found a place to actually test the conductivity. Every batch is tested just to make sure we're getting the right mix. Our building interfaces, the reason I point this out, our pressure is so intensified now that we actually, when we turned the system on, some of our pressure reliefs blew off, and we had water all over mechanical rooms, so we had to go through and adjust all that. If I had to do it over again, I'd have, instead of 4 heat pump chillers that are 2,500 tons, I'd probably have one of those 2,500 ton chillers cut in half and have 2 1250s. It's so efficient. There's times of the year that I could get by with one 1,250 ton unit for heating the campus. Learning opportunities, we are a university, and so we're always looking for ways to capitalize on explaining how this works to both our university, to folks outside the university. I talked with a number of colleges here at Ball State University. We've tapped our geology department to do a little bit of research on this project, including using their graduate students to monitor wells around our borehole fields so we can keep an eye on what's happening with the temperatures and the water flow. And we are also now in the process of arranging for, you may be able to find it on our website, I think the information's out there, every year around February, this year it's 2013, it's going to be February 11th, 12th, and 13th, we're going to hold a geothermal nexus. We're asking for papers, we're bringing in designers, we're bringing in installers, and it's going to be a Monday, Wednesday, Thursday sort of opportunity. It's going to be design, installation, construction, something of that type of arrangement, so that we can continue to spread the word on how geothermal works and what it can do for other entities that are interested. And I went over my time, but that's it.
Jim, thank you so much. It was a really excellent presentation, I have to say, at least for me. I found it interesting to hear how Ball State went through the process of deciding that geothermal made the most sense. So thank you for going into that detail. We've got a number of questions in, so I'm going to start off with one from Robert. He asks, what sort of assessment did you need to make of the site geology to determine well depth and spacing? And then also, if the ground temperature started to rise or fall, what would be your response?
I'll take the first question. That is, we actually installed several test wells. In other words, installed a real well, did the conductivity testing, had the results provided to the designers as they use their software programs to determine spacing and lineal feet. And so those test results were critical in determining how we went about the spacing and the depth, the conductivity rating, and so forth. To the how do we adjust, I didn't have time to go into it, but I did explain early on we are keeping our natural gas-fired boilers for several reasons. There are some processes on campus you can't convert to 150-degree water, so we do need some steam for dining facilities. Plus, we sell steam to a hospital, Ball Memorial Hospital across the street. They need, about 50% of their need is steam. They can't go to 150-degree water. We'll have our gas boilers as peaking, and so it'll be there to peak, as well as if we find we're inserting too much heat into the ground, I'll back away from the geothermal a little bit and make more steam for buildings, a certain number of buildings on campus. And so we can reduce that thermal energy flow into the ground in that manner. On the are we overheating side, we are, as part of our design, installing a backup cooling tower. I hope I never run it, but it's there just in case we need it. Matter of fact, we also need it during the transition because we're converting our old chill plant to a geothermal building. And we were tearing off our cooling tower, so I'm going to sit on the ground, a portable unit, and then mount it on top of the roof when we're done. That cooling tower will provide us the ability to dispense heat if, in fact, we find that we are somewhat cooling dominant in that manner and we're putting too much energy in the ground. So we'll watch the flows, the efficiencies. Our geology department will give us some data, and we'll modify based upon what we see, and we'll have steam, gas backup, and cooling tower backup.
Great, thank you. Andrew asks, was permitting difficult or time-consuming for this project?
The interesting thing about permitting is that in the state of Indiana, there isn't a lot of requirement for permitting, meaning that if you go to the northern states, I think they're a little more ahead of the curve, and there are a little more, and I haven't evaluated, so I really can't give you a lot of detail, requirements that one has to go through to install a geothermal system or reach into the ground. In Indiana, there is no such requirement. We do have to log our wells, much like they were water wells. We do have to go through all the construction requirements with runoff and so forth, but we are not subjected to any other type regulations at this point in time.
Interesting. I think that's maybe not the case in most states.
No, it's not in a lot of cases. And it may change in Indiana, I'm not sure.
Yeah. So we've got time for one more question, and then keep your questions coming, everyone, and we'll have some general Q&A at the end. So this question comes from Ram. Can you talk about how you create 150-degree water when the ground temp is about 55 degrees?
It's through that refrigerant compressor system that in a two-stage approach would make the temperature of the water hotter depending upon the temperature of the refrigerant flow. It's much like your refrigerator. The best way to explain it, and instead of getting a lot of complicated jargon, your refrigerator. Your refrigerator, if you open the door, you've got whatever it is, 40-some degrees inside. So you ask yourself, why then can I reach out the back of my refrigerator and feel that hot air coming out when I can reach in the refrigerator and I got cold, which is what it's supposed to be doing? Well, that's what this equipment is doing. It's actually extracting heat out of the refrigerator and intensifying it through the refrigerant process, that compressor cycle, and it blows it out the back of your refrigerator. And I don't know what the temperature is, but it's a whole lot hotter than what's in your refrigerator. So it's that two-stage refrigerant process that R134A is what we're using that allows it to ratchet it up to 150. And this same company makes equipment that can produce 170-degree water, but it's a little more electric intensified, I should say. That's the right word. But we found that we could get by with 150, so we didn't go to the next stage.
Perfect. Well, thank you again, Jim. Please stay on the line, and we'll get some more questions to you after Ken goes. So I'd like to introduce our next speaker. His name is Ken Smith. He's the president and CEO of Evergreen Energy. Mr. Smith serves on the board of directors of the International District Energy Association. He received a Bachelor of Science in Electrical Engineering from North Dakota State University and an MBA from the University of St. Thomas, and is a registered engineer in several states. So Ken, if you're ready, we're going to turn it on over to you.
Okay, very good. I'm going to get my screen loaded up here. I should be ready to go. Can you see it?
Perfect. Yep, we do.
Okay, very good. Well, Sarah and Devin, thank you very much, and thank you for the opportunity to share our story with you today about St. Paul, but also to share the story about what is happening in some other communities that I think would be of interest to all the listeners today. I'm coming from, as you said, from sunny NREL. We're coming from sunny St. Paul today. It's about 50 degrees, so it's a gorgeous day here in St. Paul. So I'm going to tell a little bit about the St. Paul story, and I share our story enough that I don't always assume that everybody knows what district heating and cooling is. So basically, a community-scale heating and cooling system is where you have an underground network of piping that's connecting the buildings together, and you're aggregating that thermal load, much as they did in Ball State, to then serve it with a variety of energy sources. And the beautiful thing about district energy is that you can plug in a whole variety of technologies, whether it's geothermal or some more traditional sources of energy, or including solar, which we have done here in St. Paul. And the nice thing is that you can, because you have that flexibility, you can get to a stable rate, which we have been able to produce here in St. Paul for our customers, and have a high degree of reliability. The key is density, and it can be for a community that's small or large. So a large city, like you have in New York City, to a smaller community such as you have in Montpelier, Vermont, where they're putting in the district energy system. The model that we use is an integrated energy system model that we follow here in St. Paul, which we have both heating and cooling, both hot water loop. We run our hot water loop in the wintertime at 250 degrees, and we drop down to 180 to 190 in the summertime. And then we have a chill water loop that's running at 42 degrees year-round. We have both heating and cooling customers year-round on the system. In it, we can then integrate in a variety of energy sources, whether it's traditional sources using fossil fuel, natural gas, and so forth, or technologies that would allow you to utilize biomass or biogas or solar. And also, you can integrate in storage. And so you can integrate in either chilled water storage or integrate in hot water storage that allows you to increase your reliability. It also allows you to produce energy and off-peak, particularly on cooling, which can be a great benefit to the overall system and to the electrical grid that you're connected to. In St. Paul, we started our system, really got started out of the 1970s as a result of the energy crises, the second energy crisis. You had community leaders that came together and said, we need to do something different. We were experiencing high energy costs. There was an old district energy system that was a steam system at the time that was quite inefficient, and it was entirely fossil fuels. And so from the mayor of St. Paul to folks at the state and business leaders and BOMA, as Building Owners and Managers Association, including the Department of Energy and the Oak Ridge National Labs, who got involved in determining the best approach to utilize here in St. Paul, and that was to put in hot water piping system modeled really after what was being done in Europe, and then particular in Sweden at that time. Started serving customers in 1983, and then in 1993 decided that we would move to cooling, and so we put in a cooling system that serves a good portion of the downtown businesses. And again, it was the leadership of the board at that time coming together to solve a problem, and that a number of the buildings in downtown St. Paul utilized ground source, basically groundwater to cool their buildings once through and then dump it. And that was then the legislature of the state of Minnesota decided to move away from that practice. And so you had a number of buildings that were going to be looking for a solution to cool their buildings. They looked at either having their own systems or connecting up to a district energy system, and that was the solution that was provided. So that started serving customers in 1993, and today we heat over 80% of the buildings. This is not all of the buildings on the system, but all the buildings in green are on district heating and or cooling. It's a little over 31 million square feet of buildings that are heated, and just under 20 million square feet that are cooled. We have all 4 hospitals. We have the state capitol, the Capitol complex. We have a college, hockey arena, Fortune 500 companies, so companies such as Ecolab, Securian, Travelers, all names that we've heard of are all on our system. And so it's a very diverse customer base, including residential, including not single-family homes, but multi-tenant residential, mixed-use facilities, restaurants, hotels, you name it. We have it on there with the exception we don't have a lot of industrial. We had more industrial in the past and would like to see more industrial on the system. One of the beautiful things about hot water is you can go much greater distances, and so there's no reason that we can't go several miles from where we're located today. The system today is the largest hot water district energy system in North America. We have just over 20 miles of hot water piping. The chill water system is quite a bit smaller than that. So in the density of the chill water is primarily in this area, including up to the Capitol and the region's hospital. We have multiple plants on the system, where you have the main plant, which was located down here by the river, where we do both heating and cooling. We have a cooling plant that's located on the north side of the city. But we also have heating and cooling equipment located in other buildings that is integrated into the district energy system. They can either provide capacity when needed or backup. For example, Regions Hospital, both their boilers and their chillers are interconnected, and they provide both capacity and backup to the rest of the system. One of the goals of the leaders when they came together was to provide stable rates. They wanted to have energy efficient energy production, and they wanted to have flexibility in the fuel sources. And so over the 30-year history, next year is our 30th year, in 2013, our energy costs have been below inflation during that entire time. We've also had the same experience on district cooling. And so customers that connected very initially and are connecting today are paying less cost year over year than the rate of inflation. One of the technologies we've integrated in is thermal storage. We actually have two chilled water tanks. This is the largest of the tanks. It's just over 4 million gallons. We have another little over 2 million gallon tank located closer to the larger plant. And this allows us to produce chilled water at night. So we move about 9 megawatts off peak from day to night, which is a great savings of cost for our customers, and it's a great benefit to the electrical grid, if you will. It acts almost as like a smart grid technology. That you're able to store that amount of thermal energy, and then we allow it to come down during the day when in the heat of the day. What we have found in the last few years is that it is really a benefit to us during extreme weather events, and we've seen more and more extreme weather events, particularly in the last 5 years, higher dew points. Not this past summer, but in 2011 we had dew point of 84 degrees. We've had this past summer in 2012, the entire month of July was the hottest on record, averaged over 90 degrees. And so there are times when it puts great stress on systems, particularly when you have the higher dew point. So dew point of 84 degrees would be like the Amazon rainforest, to give folks an idea. And so actually traditional cooling towers can have great difficulty operating in that. But because we have thermal storage, we were able to meet all the needs of our customers on those days, and they did not even experience any challenges with that at all. Which is very important because we have a number of data centers on our system. So you have Fortune 500 companies and the state and others. So you have small and large data centers that are reliant upon our cooling. We've also integrated in combined heat and power. We produce 25 megawatts of electricity that is sold then to the local utility out on the grid. And we utilize biomass, urban wood waste, as the primary source of energy. So it's a plant that utilizes both biomass and natural gas. It can utilize 100% biomass, and we do operate with 100%. But most of the time we're operating in the 85% range. And this is a picture of the plant here located right downtown. This is actually that 2 million gallon storage tank that I was sharing with you earlier. It is, as I said, right downtown St. Paul. This is the combined heat and power plant located here. This is where the truck deliveries come into the facility. If you consider both the thermal energy that we use and the electricity that would have been coal-fired, by displacing that, we can reduce greenhouse gas emissions up to 280,000 tons per year. Basically what we're doing is we're using urban wood waste, and I'll share with you in a moment where that comes from. But urban wood waste that comes from a variety of sources that is then brought to a plant as wood chips and so forth. It's burned to make steam, produces electricity that's put to the grid, and the waste heat, which would be normally dumped via cooling towers or into a river, as you'd see in a lot of power plants, in a body of water, then is utilized to heat the downtown area. It comes from a variety of sources. It can come from wood residuals from manufacturing processes. We can utilize pallets. Most of it is tree trimmings, storm damaged diseased trees. We now have emerald ash bar that has moved into the area, and those kinds of sources are given priority so that it does not spread. And then also trees that are removed as far as land that is being restored. So you have invasive species. We partnered with the Minnesota Department of Natural Resources that they will remove these species from lands, and then we utilize it as fuel. It's been a great partnership. We are in an area, this is an NREL map that's quite familiar, I'm sure, so we have a lot of biomass located in Minnesota, but there's great biomass potential in many other states as well. And you mentioned earlier the Montpelier-Morvant utilizing biomass for their district energy system. You also have Seattle Steam is utilizing biomass for their district energy system as well. This is our solar thermal project. It went operational in 2011. It is the first of its kind to be integrated into a district energy system in the U.S. It's sized for 1 megawatt thermal. We actually have, and that's peak. We've experienced much higher than that. Today we would rate it about 1.25 megawatts thermal. This was a project that was done in part through a grant through Department of Energy. We competed through the Solar Americas Communities program and then won a grant for this project. It's very unique in that it is integrated both into a building that's heated and cooled with district energy, and this is integrated into the hot water system. So in the morning when the sun first starts coming up, it starts to warm up or preheat the domestic water used in this building, and this building is the convention center, the River Center Convention Center in St. Paul. And then it starts to heat the building, and when there's excess energy, it then puts it out to the hot water grid, which makes it very unique. When we modeled this, we expected to only have solar export, not in the wintertime, but in the shoulder seasons, and particularly in the summer. But we've actually, last winter, exported every month of the year. And so it's been a tremendous project for us. As we look at this project, one of the things that we want to make sure that we do is we account for carbon emissions reduction, for example. We took into account also the electricity, so there's pumping and so forth. And so it's not just a matter of the solar energy that we gain in a hot water loop, it's also what are we having to account for example, the electricity for the pumping and the controls that we also included in our calculations. This is what we have termed the Science and Sustainability District. This is where our combined heat and power plant is located. You have, this is the City Hall, a library, finest one, if not the best hotel in the Twin Cities, one of the best, and this is the convention center. So it's all very close proximity. This is the Science Museum in Minnesota. And in this little district right here, you've got solar PV, pretty large scale. This is the roof where our solar thermal project is located, and then combined heat and power. And there's really only one place that you can go in North America to see all these technologies integrated into a system, and that's here in St. Paul. As a result, we've had visitors, much like all states experiencing. We have visitors from around the world since 2008. This says 47 countries, I believe. We're up to 54 now. Visitors from different countries since 2008. And we certainly welcome those who are listening to come to St. Paul. We love to share our story and share what we've done, but also share with you how you might be able to move forward in your community. So I want to shift gears into the next part, just community energy planning in general. Really, and we have, through Evergreen, we do a lot of work in other communities, helping them move forward with their systems, and it's all along this timeline, both in what we do in here in St. Paul, but other projects as well. And so in some ways we have a little bit of a unique experience of what's happening, and you're seeing that community energy systems are really becoming a preferred solution. They're proliferating in North America, throughout the U.S. You're seeing a tremendous amount of communities coming together, trying to figure out the best way to move forward. And they're looking for energy efficiency, they're looking for energy security, they're looking for ways to keep dollars local in their community and to reduce their greenhouse gas emissions. One of those communities is in Arlington County, Virginia. where they have been moving forward with the Integrated Energy Master Plan. This is for Crystal City, so if you're familiar with Washington, D.C., it is right across from Reagan Washington National Airport, and it's a very dense area with a lot of offices and hotels and restaurants and so forth. And this was the first area of 3 that they have done the study for. And really they came with the goal of increasing energy efficiency, reducing greenhouse gas emissions, and they want to have economic vitality in this area. And this project is quite exciting. It is a consortium of Arlington County, together with Washington Gas Utility, and then also with Vornado, Charles E. Smith, which is a building owner, developer that has about 30% of the properties. They have a great website too, by the way, so if you want to learn more about that, I would encourage you to check it out. This is a project that we've been involved in Minneapolis. This is the North Loop area. You may have heard of Target Field, which is the new home of the Minnesota Twins. And immediately next door to it is a waste-to-energy facility that's only generating electricity. And that facility then was dumping the heat, basically through cooling towers. And so we got involved with Hennepin County to look at how could utilize that thermal energy that was being lost into this North Loop area, which is an area that is really beginning to develop and emerge, particularly with the development of the new ballpark. You can see down here in the lower right-hand corner is a new transit facility that's going to be built, and we've designed hot water, taking the cooling tower water and using that to do snow melt for platforms and driveways. And we've also then designed a district energy system, or planned a district energy system for that North Loop area that's both heating and cooling, utilizing thermal energy that was previously being dumped from the waste energy facility. Another community I would encourage you to take a look at is in Markham, Ontario. After an ice storm several years ago, that community came together and said we needed to do something different to have more reliability and security in our energy systems. And they had, it's an area just north of Toronto. And so the city then began a district energy company, and it's a very fast-growing area. They are now the fastest-growing district energy system in Canada. They'll be rivaling us pretty soon for the largest hot water district energy system in North America. They're doing great things up there where they've integrated in combined heat and power in multiple locations, utilizing natural gas as their energy source, but they're now looking at could they utilize biomass and solar thermal. And as a result of this, they're seeing one of the hopes they want to have is economic development in this area, and that having this form of energy system, a community energy system that would provide affordable, stable rates to the customers would be a draw, and it indeed has been. So one of the things that communities can do is to analyze what they have as energy sources. And this is a project that we did. This was also funded through a Department of Energy to do an analysis along a corridor of looking at where are there energy sources that could be utilized. For example, where you have a college and university that maybe has boilers and chillers. In this case, we were looking at heating. It could be an industrial facility, say a paper or recycling plant or a steel mill, where they have excess thermal energy, and where could it be used around them. And this was an analysis that we did here in the Twin Cities to analyze where are the potential hot spots where you could begin a district energy system and utilize infrastructure that's already in place, whether it's boilers or chillers or combined heat and power facility, or like I mentioned for the Minneapolis North Loop, where you already have an electrical generation facility in place and you have excess thermal energy that could be utilized. One of the common themes that we see is that community energy, district energy is happening on the local scale, often led by local units of government, but with the involvement of businesses and utilities. And it really takes, I like to say that community energy it's just that. It's community energy. It takes all of those players to make it go. And so you're seeing that happen in a number of communities. You're also seeing a widespread use of public-private partnerships where local units of government working with businesses to try and make these things happen. We're looking for environmental and sustainability goals to reduce greenhouse gas emissions and reduce emissions overall, as we experienced at Ball State and we've experienced here in St. Paul. And having the community competitive, that it's able to have energy efficiency and stable rates to draw businesses and have businesses save money and create jobs and encourage economic development. But then also to secure the community and make it more resilient with a reliable energy supply and flexibility and integration of local energy sources. Particularly what we've done here in St. Paul then of integrating in solar and biomass, where biomass is our primary source of energy and is over 60% of our annual energy basis. What you're seeing is a lot of change in energy in the U.S. Particularly we have our sources of supplies, petroleum, natural gas, and so forth, but you also have the uses. And what most people don't realize when they look at this diagram is that about between 30 and 40% of the energy used in this country goes for the heating and cooling of buildings. It's the thermal energy. And while there might be changes in what's happening in the various supplies, whether it's coming from renewables or from natural gas, there's also an opportunity when it comes to the utilizing that in a variety of areas. And you have one of the great opportunities that we have in this country is our centralized generation of electricity is about 33% efficient, which means, as Jim was explaining earlier, for every dollar that we put in, you're basically getting 33 cents out. And we have a great opportunity in many areas to improve the efficiency of our energy system by integrating in with district energy systems and utilizing waste heat from electricity generation to produce both heating and cooling and recovering that heat and making beneficial use of it. And then get efficiencies of 80% or greater. For those that are new to district energy, there's a tremendous amount of district energy in North America. This is somewhat dated. There are more systems than this because you have pretty much many colleges and universities like Ball State have district energy systems, but you have smaller community colleges and so forth which have systems as well that don't show up on this map. And so there's opportunities to integrate in a variety of energy sources and expand the use of district energy and improve the overall efficiency of the energy system. I want to give you an example of what's possible. This is a diagram from Sweden. Much like we had experienced here in St. Paul, when you had the second energy crisis in the 1970s, Sweden was impacted. They don't have fossil fuels, and so they import much of their energy, and as a country they were, for district heating, which is used quite significantly in the country, is about 95% of their energy was coming from oil. And as a country they decided to do something different. And you can see from 1980, basically by 1995, they had moved dramatically away from fossil fuels to renewable energy sources by integrating those energy sources into district energy systems. That's what makes it such a great technology. And so they had waste heat integration, heat pumps, as you're seeing in Ball State, geothermal. You're using heat pumps where you could use heat pumps, latent heat in sewage, for example, and utilize that as a heating source. Biomass then is being a very large component of their energy, and that today you can see that it's under 20% of their energy sources are coming from fossil fuels, where most of it is coming from renewable sources, including biomass. On scale, Sweden is approximately the same size as Minnesota and Wisconsin, geographically and population. And this represents, as I mentioned earlier, we have the largest hot water district energy system in North America. This represents about 160 times the system we have here in St. Paul. So it's a tremendous amount of square footage that's heated with district energy and utilizing primarily renewable energy to do so. And so coming back to the integrated diagram to wrap up, this is a while we use this in St. Paul, this can be utilized in a variety of communities. Maybe you have more heating needs than cooling, or you have more cooling needs than heating. Regardless, you can integrate in a variety of technologies by having this district heating and cooling system in your community. And this kind of technology allows you to integrate in energy sources that accomplish things on a city scale that you could not otherwise do on an individual building basis. And that makes it much more efficient and resilient. And with that, I will take any questions that you have.
Thanks, Ken. That was really, really good. Catherine has a question that Jim mentioned that permitting wasn't as burdensome in Indiana as it can be in other states. Can you talk about the permitting for the renewable energy components in your case?
For the combined heat and power, it is a combustion plant, and so you're combusting biomass, and we are located right downtown. So the permitting took some time. It was at least a couple of years, but in the overall project schedule, it actually took quite a distance of time to get the power purchase agreement with the utility. And so it wasn't burdensome. It's a very thorough process that you need to go through. So on the biomass, it took approximately 2 years, just under 2 years. For the solar project, in that case, you're really just going through the local building codes, but we end up spending a lot of time with community leaders to make sure the aesthetics were right and so forth. And so it wasn't a permitting challenge for the project. We just wanted to make sure we were being a good neighbor by putting the project on the convention center.
Thank you. So we have a question from Miho, and Miho asks, who owns the system, and do customers pay the city directly?
Okay. District Energy St. Paul is a 501c3 nonprofit utility. That's very unique. So it's a private nonprofit. It's not owned by the city. It really operates much like a co-op. And so it sends out the bills to the customers. The customers pay their bills to District Energy St. Paul. We have an agreement with the city that allows us to utilize the city right-of-way, the streets and sidewalks and so forth. Any public right-of-way, we can utilize that for the routing of our heating and cooling piping. And to do that and have that privilege, we then have a franchise fee that is added to our bills.
Okay. Pamela asks, what suggestions would you have for cities looking to incorporate renewable energy into a district energy system?
Well, if you have a district energy system in place, it depends on what you have for a transmission medium. If you have steam, it's somewhat difficult. If you have hot water, it makes it much more flexible because you're operating, for example, the solar project, we're producing upwards of 200-degree water with our solar panels, and so we're able to integrate that into the hot water system that we have. So it really takes, you have to look at what do you have for distribution sources. If you're doing chilled water, for example, you could do solar thermal cooling, which is a technology we'll be looking at. You could also use electricity to generate it through electric chillers or heat pumps or so forth. So what I would look at first is where do you want to go with it? What kind of transmission medium do you have, whether it's hot water, chilled water? Steam is not as flexible, and so I would say to the extent possible move to hot water sources so that you can plug in more variety of sources. The other thing is look at what you have locally. Is there an energy source around you? For example, the wood that was used here in St. Paul, the urban wood waste was actually a disposal problem. And so tree trimmings and so forth, there was only so much mulch that folks wanted to put around their flower beds and around their trees. And so it was something that communities were challenged with, how to dispose of it, going to landfill and so forth. And this provided an outlet for that excess materials to become an energy source for a community. So really look at what you have locally. And I would challenge you to look even beyond renewable. It may be that in your community you have say, a power plant, or you have an industrial facility that has excess waste heat that could be utilized as an energy source in that community, and it really doesn't, it wouldn't produce any more or very low amount of emissions just to capture that and utilize that energy.
Thank you, Ken. I hope people on the call and attending found that helpful for systems they're looking at. Jim, we have a question for you from Marty. Can you give us an idea about the time it takes to build a geothermal district energy system like this?
Yeah, there's a story behind that answer. Being the engineer I am, and I run construction, I wanted 10 years. And I got talked down to 6, and eventually I cooperated and settled on 4. And so what that really means is if we had all our funding in place, running the project as we did, which was a process of simultaneously running borehole installations, installing distribution lines, building a new district energy station, modifying buildings. We ran all those concurrent. You can, in our case, over our 7 million square feet and 1,000 acres, I could have easily gotten it done in 4 years if all the funding would have been in place. It was a challenge working with a campus as it remains in operation, but what you would do in our particular case, you would capitalize on the summer months when there are very few students on campus and do as much as possible. And then throughout the academic year, which I'd call the fall, spring semesters, you'd do as much work as possible out of the way, out of sight, and in places where it doesn't impact the campus as possible. And that's how we would have accomplished it. It was phenomenal to get half of it done in 2 years.
Okay, thank you, Jim. Ken, we have a question for you from Robert. He asks, what was the selling point for convincing the various facility owners to connect to the district system, and was there an incentive in place?
There weren't incentives in place. When initially for the heating system, customers had to sign on to a 30-year contract, and so that, as you can imagine, was maybe a little bit of a challenge. But you had, the promise was that you were going to experience stable rates, you're going to experience fuel flexibility, you were going to experience a very efficient energy system that would continue to move forward and integrate in a variety of energy sources. And so it really took local units of government, the mayor and so forth, that stepped forward, said they were going to connect their facilities, and you had some of the business leaders who said, this makes sense for our community, that we're going to do this, and so they signed their buildings up, and that really got the ball rolling once they did that. So there was no incentives in place for them to do that. All of the customers signed the same terms and conditions, if you will. It's a customer contract. The only thing that's unique about it is what is unique to that particular building, and so you capture that in the contract. There were some nonprofits that were somewhat challenged to come up with maybe some of the costs that they had to do inside of their building, and so there was a foundation that came forward and put in place some loans that were then able to be tapped into, and they would pay that loan back with savings that they would experience by being on the district energy system. Today, it's even with natural gas prices where they are, we still are, we're competitive because of our fuel flexibility, because we're utilizing biomass with the natural gas prices. And customers, now we have a track record. They can see that we have done exactly what we intended to do, and that was produce very stable, affordable, reliable energy for them to meet their energy needs.
Great. Thank you. So I know we're just about out of time, so we have a lot of good questions, but we're only going to get to one more, and I'm going to ask this of both of you. Are you finding that renewable portfolio standards are proving overly necessary for development of these systems? How significant are these standards when making market decisions? And this comes from Charles.
I'll take the first shot at that. Yeah. the Renewable Portfolio Standard, our combined heat and power plant that we have here in St. Paul, there was a mandate for a certain amount of biomass to be put in through Renewable Portfolio. It wasn't a Renewable Portfolio Standard at that time, but there was a mandate for, I think it was 105 megawatts of electricity from biomass, and this is one of 3 projects that were then contracted with to provide that. And so that certainly is helpful when it comes to the economics of it. But whether you're using renewable or you're using natural gas, it really gets down to having some kind of a power purchase agreement when you're generating electricity in order to make that happen. The solar project, there's no portfolio standard. So I think it's helpful, particularly when you have the lower natural gas prices, but I don't know that it's completely necessary. What is necessary is we need to have an energy policy that defines basically the rules and defines where we're going to get our energy sources from. And I think that will help diversify our energy portfolios and will send clear market signals.
And this is Jim. I don't think I can improve upon that answer, Ken.
Well, that's a great way to end then. Thank you so much, Ken and Jim. We really appreciate you taking the time out of your day to talk about the projects in Indiana and in Minneapolis. Everyone else, thank you for participating and thank you for sending in excellent questions. I apologize we weren't able to get to all of them. Please be sure to complete the survey that pops up when you log out, and we hope you're able to join us for the next ComRE webinar, which will be on January 15th, and will focus on successfully developing and implementing RFPs for renewable energy projects. Due to the holiday season, we aren't going to have a webinar in December, but we do hope you're able to join us